So, welcome to today's lecture. We are going to cover laminar slug flow. Okay. So, if you look at the screen, this will be the laminar slug flow. So, let us write down first the key concepts. We are going to say that Prandtl number almost equals to 0. Okay. So, that means the flow is almost equal, the flow velocity at any point is almost equal and uniform to the inlet flow condition, right. So, this also means that the velocity boundary layer or the hydrodynamic boundary layer takes a very long time to develop. So, it does not get developed within the length. So, the entrance length is basically huge. Not only that, the boundary layer is always thin for the length of the pipe or the duct that we are concerned over here. So, of course, the thermal boundary layer develops much faster than that. It is a velocity boundary layer which is very thin. Okay. So, it is almost like a scenario like this, that if this is the velocity boundary layer, there will be a boundary layer obviously. Okay. So, the velocity is kind of something like that. Okay. So, it is very top hat kind of a profile, and it is almost equal to the velocity u for all practical purposes. It is never quite true, but since the thinness of the boundary layer is so thin that we can effectively imagine that your velocity is almost the same as u. Okay. So, we also take that it is a constant wall temperature. The rest are usual assumptions. That means T naught. Okay. There is a uniform inlet temperature. Which is T in. These are almost the same as what we had earlier, right. So, only thing is that instead of a fully developed velocity profile, which is a function of r, here we have a constant value of the velocity, which is u, mainly because of a situation like this. So, this happens a lot in the food industry, because if you are trying to push say solid food or semi liquid kind of a food through the pipes, okay, there usually the boundary layers are very thin. As a result of that, your velocity is kind of uniform, okay, across the cross section. That means the r dependence is not there anymore. That is what I am trying to say. Okay. But if the pipe is very long, ultimately this velocity profile will develop. Okay. The thinness assumption is going to be no longer valid, but for all practical purposes, for the current situation that we are dealing with, this pipe length is short enough. It is still long, but short enough relatively, so that the velocity remains the same. So, as before, we now define our non-dimensional numbers or non-dimensional variables. R bar is equal to R by R naught, X bar X by D, RED into Prandtl number. If you recall from the previous lectures, so G is the non-dimensional variable, which is T minus T naught divided by T in minus T naught being the wall temperature. T naught is the wall temperature, the inlet temperature is T in, right. Remember that we got from our entrance length analysis that X bar is equal to X by D, Reynolds number, Prandtl number. So, the energy equation will be U by alpha dt by dx right. That is the standard energy equation that we had, right. Of course, here we are putting u as the velocity instead of the fully developed velocity profile that you had earlier. So, u by alpha T in minus T naught divided by d RED into Prandtl number dg by d x bar 1 by R naught square minus T naught. right, after substitution. So, let us move to the next one. So, if you take the relevant parameters out, or it will be 1/4 dg by dx bar d square g by dr bar square plus 1 by r bar dg by dr bar. Okay. Now, as we know that 1 by x is sometimes written as 1 over the Great's number. Okay. This is written in some of the books, okay, in other literature you will find, but essentially this is just the reciprocal of the normalized distance. Okay. So, the boundary conditions are g equal to 0 at r bar equal to 1, dg by d bar equal to 0 at r bar equal to 0, g equal to 1 at x bar is equal to 0. You can easily see the veracity of this thing. Okay. So, at r bar equal to 1, okay, where t is equal to t naught. So, therefore, g should be equal to 0, right. R bar equal to 0 should have an inflection point. So, therefore, dg by dr should be equal to 0 over there because of the temperature inflection point. And at x equal to 0, that means x bar equal to 0, that is at the point of the inlet, right, okay, where t is basically equal to t in. So, therefore, g should be equal to 1. So, these are the three boundary conditions that we have. Once again, as I told you earlier, that this equation that you have represents unsteady heat conduction equation, where x bar basically doubles up as the time scale. So, normally in a heat conduction equation or a transient heat conduction equation, right, okay, or 1D transient heat conduction equation, that is what it is, right, in of course cylindrical coordinates, you would have that there will be this term will be basically your time, and this will be the corresponding spatial coordinates, right. So, here of course the x bar is doubling up as your time. So, okay. So, as the axial length is basically what your time scale is all about. Okay. So, it is very equivalent, okay, though the problem is not the same. Okay. So, it is basically an interesting observation nonetheless, that where your 4 x bar is basically like your elapsed time, got it. So, 4 x bar is nothing but like your elapsed time. So, it represents or resembles transient 1D heat conduction equation. Okay, got it. So, the solution, okay, will be kind of similar. So, let us write it in a more put the Great's number. This is the most compact way of writing the same equation. Okay. Once again, you use the separation of variables. So, your g will be basically r1 r bar, z1 4. Okay. So, one is a transient part and one is the spatial part correspondingly. Well, in this case both are spatial, but one is like time. Okay. So, if once you substitute it back into this particular equation, what you have is basically okay, that is what you have, right, okay, or right. Once again, I have told you the significance of choosing minus lambda square. That is because of the reason, otherwise you get a exponential term which increases. So, here the solution has to be always bounded, right. So, you cannot have that exponential increase, otherwise mathematically speaking plus lambda square is an equivalent solution. So, but in this case from a physical point of view it cannot be the case. So, that is why we have written it like that. Okay. That we covered in our earlier class when we are doing thermally developing flow, right. So, it is the same analogy actually works here. Okay. So, or Z1 is equal to C1 exponential lambda square by Gz into 4, right. So, that is the first solution that you will have. Once again you can see that it is exponential and it is negative. So, therefore, with time, okay, or with distance, okay, this solution is bounded. On the other hand, okay, so R1 is basically C2 J naught lambda bar plus C3 Y naught lambda bar, okay. That is the solution. These are basically Bessel's functions. Okay. Of course, as you can see it is of the order 0, so 0 order, right. Okay. First kind, second kind. Okay. So, J is the first kind, Y is basically the second kind. Okay. So, that is the solution that you have. Okay. But once again, one interesting thing about this particular solution is that let us look at the companion PPT. So, if you look at now a situation like this, right, where we have basically plotted the functions, right, and I have marked a few things over here. So, as you can see that at this particular term, okay, y is basically the second kind, okay. At 0 it goes to minus infinity, okay. But you know that your G, because R is basically a combination, if you recall what we did just now was basically that you had R, right, you had R1, if we write it here then it is equal to J naught lambda R bar plus C3 Y naught, okay, lambda R bar, correct. These are the two things that we had just now, right. Of course, as you can see at R equal to 0 therefore, or R bar equal to 0, right, this particular term basically blows up, right. That is because it goes to infinity, right, from what you can see over here there is an infinity, right. So, in order to assure finiteness of G, because what is G? G is basically nothing but R1 into Z1, right. That is G, right, R1 into Z1 is G, right. So, in order to keep G finite, okay, finiteness of G, what we can technically assure in order to do that is basically to make C3 equal to 0. So, C3 has to be equal to 0, because otherwise this entire term will blow up at R bar equal to 0, right. So, that is the logic that we will apply over here and make that C3 therefore should be equal to 0, correct. Okay. So, moving on, going back to our journal. So, therefore, your R here in this case C3 must be equal to 0, right. Okay. So, therefore, your total G will be now C exponential 4 lambda square by Gz into J naught into lambda R bar, right, combining the two constants, okay, and assuring that C3 is equal to 0, right. Now, of course, you have G equal to 0 at R bar equal to 1, correct. Okay. So, this of course implies that J naught at lambda, okay, is equal to 0. There is many values of lambda, right. Okay. So, therefore, your G should be equal to n equal to 1 to infinity C n exponential minus 4 lambda n square G z J naught lambda n into R bar, okay. Got it? Okay. And j naught into lambda n is equal to 0. Got it? So, multi-values of lambda n. Okay. Also at 4 by gz is equal to 0, g is equal to 1, that also we know, right. So, therefore, n equal to 1 to infinity Cn j naught lambda n r bar is equal to 1. Got it? Okay. Now, taking this forward, okay, therefore, G is equal to 2 into n equal to 1 to lambda E 4 lambda n square into Gz j naught lambda n r bar divided by lambda n g1 into lambda. Okay. This is of the first order, okay, Bessel's function of the first kind. Okay. So, Gm, which if you recall is the mean temperature or the mixed mean temperature, that is given as T naught minus Tm divided by T naught minus T in, right. Okay. So, that is a mixed mean temperature that we have. Okay. Got it? So, Gm, in order to evaluate that, okay, we already know how to do it. It is integral 0 to 1 G r dr, right. That is what it is. So, 4 0 to 1 exponential minus 4 lambda n square by Gz r bar j naught lambda n r bar lambda n g1 lambda n into dr bar. Therefore, Gm would be equal to 4 okay, that is Gm for you. Got it? Okay. So, that will be Gm, that is the mixed mean temperature what we defined. Similarly, your Nusselt number, which will be one of the most important parameter over here, okay, will be, see, all these series converges pretty fast. So, you do not need to consider a whole lot of terms, right, to get convergence. Okay. So, this is the value of Nusselt number at any point, right. Obviously, as x bar approaches infinity, right, okay, what happens is that your Nusselt number, this particular form, approaches 5.7831. It is a little higher than your other cases. That is because you are dealing with a uniform flow field right now. Okay. So, so this is the key value, and of course, we have in the PPT, we can show that this is how the entire thing actually works. As you can see, this is the mixed mean temperature, okay, and this is the corresponding value of Nusselt number. Once again, it starts off pretty high at around x bar is equal to 0.1, right. It slowly asymptotes to the value of about 5.7831. Okay, and after that it is constant, because that is the thermally developed regime. Okay, and the only thing is that here u is equal to capital U. Okay, so that is the only caveat that we have in this particular case, right. Okay, so that is interesting. So you should note the difference between this and the corresponding situation where the velocity profile was not like this. Okay. I would pose the problem because for the constant constant wall heat flux for the same situation, right, but you can solve it on your own. Once again, the flow is a slug flow. Prandtl number goes to 0. Inlet temperature is uniform. This is uniform, right. Okay, there is a uniform wall heat flux. That's the only difference, which is Q double prime. That is all. There is a uniform heat flux, which is given by Q double prime. Okay. So now your definition of G is T minus T in divided by Q double prime R naught by K, right. R bar equal to R by R naught, X bar is equal to X by D divided by RED into Prandtl number, right. Okay. Okay. So those are the things that we have. Okay. Then you have your U by alpha dt by dx is equal to d square t by dr square plus 1 by r dt by dr. Okay. The same thing is valid now over here, except now your u becomes once again capital U. Q double prime now comes over here because of your definition. This dg by dx bar, right, is equal to Q double prime R naught by K R bar square plus 1 by R bar dg by dr bar, right. Now if you take a few terms off from both sides, okay, once again your equation remains exactly the same. Of course, the boundary conditions will be different, as you know, R bar square plus dg by dr bar, okay, into 1 by R bar, right. Only thing is that, so nothing has changed as far as the equations are concerned, they still are the same, except now the boundary conditions are a little bit different. So G at x bar equal to 0 is equal to 0, that is obvious once again, okay, because your T in, T is basically equal to T in, okay, in that particular case. dg by dr bar at r bar equal to 0 is 0 because of the finiteness of the whole thing, okay, and dg by dr bar at r bar equal to 1 is equal to 1 now, okay, that is because your heat flux, okay, because you have a constant wall heat flux now, okay. This is because your k dt by dr is equal to Q double prime, correct, okay. That is because of that. So the equations, as I said, okay, the only boundary condition that has changed is this guy over here, and your definition of G also has undergone a change, right. So based on these two factors, that your G has undergone a change and your dg by dr, you have to write the flux conditions like that, okay, the rest of the problem can be worked out exactly in the same way as before, because this part of the equation does not change at all. It's just the boundary conditions now that you have to apply, and then you have to see what kind of a answer that you get, okay. So that is what is left as a task, but I have posed the problem and have shown how the problem actually works. Nothing more changes, except please note that now this is the way that we have written it, okay. So here what we do is that in this particular lecture we have covered the uniform slug flow, in which we have shown that though this is an unrealistic situation, but for all practical purposes, if the boundary layer remains small throughout the entire span of the pipe length, okay, then perhaps this is not a bad approximation, okay. It might over predict the Nusselt number by a little bit, but that is okay so long, because your analysis is very simple, right, and it almost represents like a transient heat conduction equation, as we saw, right, where the conduction term is axial conduction term is, or the time varying conduction term is basically the axial conduction term, okay. So based on this we have formulated, we have shown that the limiting case of Nusselt number, at least in the case of constant wall temperature, is 5.78, which is higher than the Nusselt number for both the other cases, okay. That means for uniform heat flux and uniform wall temperature for the fully developed thermally and hydrodynamically fully developed flows that we did much earlier, right. Okay. The solution is a little bit onerous in the sense that it involves separation of variables and series solutions essentially, right. But as we know that though there are infinite number of terms, the series converges usually pretty fast. That means the terms do not change, progressively get smaller, so that you do not have much of a change as we include more higher and higher order terms. So, within 4, 5 terms, 6 terms, you basically have convergence. Okay. So, in the next class what we are going to do is that we are going to look at the viscous dissipation part just a little bit, and we are going to pose the problem of power law fluids. That means fluids which may have which is not a Newtonian fluid by nature, right. So, they have got a power law behavior. This is not a rheological flow course. That means it is not deals with rheology or complex fluids. What we are going to do is a very straightforward. There is a lot people can spend an entire course on rheological flows, how the rheological flows actually, the convective heat transfer mode of such flows, okay, where shear is not such a simple function, okay, of viscosity. But in this particular case, we are just going to give a simple example and see how those problems can be tackled and move on. Okay, if you want a more full-fledged course, you should consult, convective heat transfer or heat transfer in the complex fluids. Okay, thank you.